Welcome back to Classical Physics, and today we are going to be talking about Newton's laws, about some conservation of momentum, some examples of that. So let's jump right in. So, Newton's laws. Our first law, see if we can see this here. First law. That's going to be an object remains at rest if originally at rest or moves in a straight line with a constant velocity if the net force on it is 0. So an object remains at rest if it's originally at rest, or it moves in a straight line at a constant velocity, and if the net force on it is 0. So there's no force on something if it's moving in a straight line and moves with a constant velocity. If it's at rest originally, then it will remain at rest. And second law is, you've seen this before, I'm sure, force equals mass times acceleration. So if you write this for the units here, I'll just go ahead and put this over here. Force, or F is force, and that is going to be, in the metric system or SI units, it's going to be the Newton. And all a Newton is 1 kilogram times meters per second squared. That is a Newton. 1 kilogram times meter per second squared. Or it's going to be in pound force. Notice I did not put pound mass. It'd be pound force. And in the future, I'm going to explain to you more explicitly the differences. And M, of course, is the mass. That's going to be in kilograms or pound mass. And acceleration. That is going to be in meters per second squared or feet per second squared. Alright, so this gives us a relationship. Not only a relationship, it lets us know that there is a direct proportionality between an object's mass, its acceleration, and its force. So it gives us this relationship. Third law. If a body if a body exerts a force on a second body. The second body exerts an equal and opposite force on the first body. So I'm sure you're probably vaguely familiar, at least, with some of these laws. So the first law, an object remains at rest if originally at rest, or moves in a straight line with constant velocity if the net force on it's zero. Basically, you've probably heard it: an object at rest stays at rest, an object in motion stays in motion unless an outside force acts on it. It's another way you could have maybe heard that one. Second law, force equals mass times acceleration. You've probably heard of that. The third law, you may have heard it, with every action there is an equal and opposite reaction. Sometimes you hear it, something like that. So whenever there's a force from one body to another body, that exerts an equal and opposite force. And that makes sense, right? So like on the third law here, if I have a box and it's resting on the ground, we have that box's weight pushing down onto the floor. That looks like a force. Okay, we have that object's weight pushing down on the floor. Well, that means there's a normal force from the floor pushing back on the box. And not only is it doing that, but it is equal in magnitude and opposite in direction of the weight of the box. Because if it wasn't, let's say there was no normal force, that means the box would just go directly through the floor. And if there was no weight on the box and there was only normal force, the box would just go flying. So if there is an object at rest there, that means that there is a force equal and opposite balancing one another. Makes sense. Makes sense to me. All right. Now, there's an additional law that most people aren't aware of that's attributed to Newton. But it has to do, let me just describe it here. So, the additional law is with the natural attraction forces between two bodies. All right, so the natural attraction forces between two bodies, that should sound familiar to you. It has to do with gravity. So, very, very big objects have a tendency to gravitate toward one another. They have a particular gravitational pull between one another. Well, this relationship was given to us that says force equals to, and this is a universal constant, I will give you that in a second, equals the mass of one object times the mass of the second object over the radial distance between those two objects squared. So, what do I mean by this? First of all, this G is the universal constant of gravitation. And this equals to 6.673 times 10 to the negative 11 meters cubed per kilogram second squared, or 3.44 times 10 to the negative 8. And that 10 did not look very good, sorry. 10 to the negative 8 pound mass per foot squared per slug squared. So this gravitational universal constant of gravitation is multiplied by the mass of one object and the mass of the other object. And the way that this kind of works is if you have this really big object and you have this other really big object, and you have from the center, in the center of this one, there's a radial, there's a distance between them, and then there is this mass, and there's this mass, and there's this gravitational constant. And so with those knowns, you can determine the force of attraction between the two. Now, let's do an example to prove the gravitational constant on Earth. That would be a good starting point. So, let's see her. Okay. Yeah, alright, so let's get the gravitational constant on Earth. So, if we know that force equals the universal gravitational constant, mass of one, mass of another, over r squared, we'll call, actually, let's just make this a little bit less ambiguous. Let's say mass 1 is the mass of the Earth. And let's say mass 2 is the mass of some object on the surface of the Earth. Let's say it's you or me, doesn't matter, right? So we've got this huge Earth. It's definitely not shaped like that, but on the surface of the Earth, you have this person, right? And so you have this distance from the center of the Earth to the surface of the Earth. That's what we're calling r. So we're trying to find out what is the pull from the Earth to that person, or basically what is the weight, right? What is the accelerational pull toward the center of the Earth on that object? It's not necessarily the weight, but that gravitational pull, what is it? So we've got the small object and it's on the surface of the Earth, and we've got the Earth itself. So the mass of the Earth, mass of the object, which is going to be insignificant basically, right? But either way, over the radial distance of the Earth squared. Now, what we also know from Newton's second law, right, is force equals mass times acceleration. So if I'm looking at the force that's being pulled on this object here, you can manipulate these equations, because you already know that this force is the force that is being, this force is the force that the object is being pulled by. And so we can say that the gravitational constant times the mass of the Earth, mass of the object, over the radius squared is equal to the mass of the object times the acceleration of the object, right? And by that, we know that our massive objects cancel. We know our gravitational constant. The radius of the Earth is, I thought I wrote it down, but I didn't. I apologize. If you write the radius of the Earth down here and square it, and you end up multiplying it by the gravitational constant, or the universal constant here, and you know that acceleration is, we're just going to call it g because it's acceleration due to gravity. That's what we're looking for. It's what we're solving for right here. So we're just saying acceleration is now g, right? So when you multiply the mass of the Earth times the universal gravitational constant and divide it by the radius of the Earth squared, what you will get is 9.8 meters per second squared, and that equals gravity. So I apologize that I forgot to write the constants down for the radius and for the mass of the Earth, but take my word for it. If you get the mass of the Earth over the radius and multiply by the universal gravitational constant, and solve for acceleration, which is your gravity, you will come up with 9.8 meters per second squared. And that's where we come up with the gravitational constant that we use on the surface of the Earth. Just for your entertainment, you could change that radius squared to, like, 3,000 or 300,000 meters or something like that. And you could just make this radius really big, right? Well, what you'll find is the gravitational constant will not go down very much. That's why it's usually in calculations we don't really care about if it's like on a mountain on sea, or sorry, if we're taking a calculation on a mountain, or if we're taking a calculation a little bit below sea level. We just use the same gravitational constant because this small of a difference makes no significant change to the gravitational number. It takes a very, very big altitude difference from the center of the Earth in order to actually impact this value. Okay, forgive me for not being as prepared as I thought I was when I put that there. All right. Next up, we're going to be talking about momentum. So now we're getting into some good stuff here. Momentum. What is momentum? I'm going to call it, or use the letter P with the vector sign on the top of it because momentum is a vector. It equals the mass times the velocity of an object. Now, in a minute, this is going to be really cool because I'm going to show you how how Newton's second law relates to momentum, or the change in momentum rather, and you can use that to determine or to find out a lot of different things, especially when it comes to rocket science and so forth, and some different things, anything with velocity, projectiles, and so forth. But anyway, momentum equals the mass times the velocity. So let's do a quick example. So let's say you have a 16-pound mass bowling ball. This is pound mass. This is not 161. Bowling ball. And it's going down the lane, and its velocity is 22 feet per second. Okay? So So what is the momentum of the bowling ball? So the momentum equals the mass times the velocity, which would equal 16 pound mass times 22 feet per second. Momentum equals 352 foot-pound mass per second. So that's the momentum. Very quick and easy example. Now, what's cool about this, and what I was saying just a second, is that now we have, momentum allows us to have we have a direct relationship basically between force and momentum. So let's write what we know here from Newton's second law. So Newton's second law told us that force equals mass times acceleration. Now, we also know that acceleration, let me write it in a different color because it looks like I'm continuing over on this. Acceleration is just the change in velocity, or let's say v final minus v naught, over the change in time. Time final minus time initial, or time naught. Right? That's all acceleration is. So if we plug in that, now we have force equals mass times v final minus v naught over time final minus time initial, or time naught. We can rewrite that as mass times velocity final minus mass times velocity naught over time final minus time initial. Now, does this look familiar? Look up here and look right here. Mass times velocity. Well, that's cool, right? So now we can rewrite this as force equals the momentum final minus the momentum initial over the time final minus time initial, or force equals the change in momentum over the change in time. So now we have a direct relationship between force and momentum. Now, that might sound cool, or it might sound not so cool to you right now. So let's do a cool example, and then we'll. All right, so we have the velocity of a rocket. Example. So the velocity of a rocket must be increased by 110 feet per second to obtain proper orbit around the Earth. So, if the rocket has a mass of 5 tons, and it takes 9 seconds to reach orbit, calculate the required thrust. Now that sounds cool, right? So how do we do that? Well, with our relationship between force and momentum. So we don't know the final velocity, we don't know the initial velocity, but what we do know is the velocity must be increased by 110 feet per second. So that means we know the change in velocity. Alright, so let's write down our initial equation. Right? Which was force equals mass times V final minus V naught. I'm just going to put change in time. So that we know is a mass of 5 tons, which is 2,000 pounds mass per ton, times 5, which is 10,000 pound mass, and that's being multiplied by 110 feet per second, and this all happens in 9 seconds. And we are trying to find out this force for the thrust. So this is a simple plug and chug sort of a problem. The force is going to end up equaling 1.2 times 10 to the 5th feet pound mass per second. So you can see how we can calculate force knowing change in velocity and mass. And what you'll also notice is this mass and this velocity is the momentum, or the change in momentum. So we know the change in momentum over time. So now we have the force. So that's cool, huh? Rocket science in physics class, that's got to be cool. Alright, so now we're going to go over the conservation of momentum. Alright, so the conservation of momentum can basically be summed up like this. So we have the sum of the momentum initial equals the sum of the momentum final. So what we already know is that this can be rewritten as the mass of an object 1 times velocity of an object 1 initial plus the mass of a second object that it's colliding with times its velocity initial, and that should be equal, since it's conservation, to the mass of the second object, mass of the first object, the velocity of the first object final, plus the mass and velocity of the second object final. So what are we saying here? We're basically saying whatever the combination of these two masses are initially and velocity, whatever the combination of those momentums initially, right before a contact, it's going to be equal to the momentum of that combination after the impact. So let's see an example. So an example could be something like a rail car with, let's say, 2,300 pound mass, and it's traveling along a velocity with 29 feet per second, right? This is rail car 1. Now we have another rail car, but it's traveling a little bit slower. This thing has a mass of 2,800 pound mass. It's also going the same direction, but with a velocity of 11 feet per second. Alright, so this is the before image, right? This is before impact. These are our conditions. Now, after impact, you will see both of these objects are now, just say 1 and 2 here, they are now combined and traveling together in one velocity. So, what is that velocity and how do we represent it based on the conservation of momentum that we just stated? So, what we'll say is mass 1, which is 2,300 pound mass, I'm going to run out of room over there, so what I'll do is I'll write it down here. So we got 2,300 pound mass, and that's going to be multiplied by our first velocity, 29 feet per second. And something to remember is the initial velocity, just think of it as just before impact. So initial is just before impact, final is just after. And that's going to be plus the mass of the second object, which is 2,800 pound mass. And that is going to multiply by its initial velocity of 11 feet per second. So all of this is going to be equal. Now notice that the velocity is now one velocity. So they don't have separate final velocities now. They've been combined and they are traveling as one object now. So what this would look like is instead of, let me get another color, instead of writing it like this, we can now write it like this. Right? Because the same velocity is being multiplied by both masses. So, if we do that, we'll get 2,300 plus 2,800, trying to write small here, times the unknown final velocity. We expand on that. Sorry, let's go ahead and do that. 2,300 times 29 plus 2,800 times 11. So I'll have 97,500. That's feet pound mass per second. Is going to equal to 5,100 pound mass times velocity final. So when we divide that out, you get your velocity final, which equals 19.1 feet per second. So this is the concept of the conservation of momentum. So what you really start with, need to understand, is the sum of the momentum of the initial is going to equal the sum of the momentum of the final. That's before impact, after impact. And you can see here we can separate that out since we know that momentum is mass times velocity. So the summation of all of the momentums that you're dealing with in the beginning and all of the momentums, the ones that you're dealing with at the end. In our specific case, we only have 2 objects, and they have initial velocities. Their mass doesn't change, and then after impact, they're going in the same direction in this situation, so they're going to have the same final velocity. If you had a different situation, let's say you had I'm just going to write it up here in the corner. If you had if you're playing pool and you had a cue ball and it hit another billiard ball, what ends up happening is the momentum transfers from the cue ball to the other billiard ball. So you can do the exact same calculations here, you just won't have the same final velocity in the 2 objects. They'll both have different velocities, final velocities. So that's the momentum conservation principle. So hopefully you understand that, and that'll help you in future physics endeavors, right? All right, until next time.